Hello everyone! We are now going to start chapter 4 of the lecture notes. In chapter 2, we introduced the general framework that we use to describe cryptosystems, and we spent some time looking at one particular example of symmetric cryptosystem, which was a affine cryptosystem on p-grams. And on chapter 3, we spent a great deal of time discussing one of the most important public key cryptosystems, which was the RSA for Ronald Shivest and Adelman, the three inventors of this public key cryptosystem. In chapter 4 now we are going to introduce the second most important cryptosystem, which is the Elgamal cryptosystem based on ideas of Diffie and Hellman. However, before we can actually discuss that system, we need to introduce one new mathematical structure that is very important, which is the structure of a group. Group is a very useful notion, even beyond cryptography. It has many applications also in machine learning, in big data, in image recognition. So independently of whether or not you're going to be working on cryptography in the future, you most likely will need at some point the notion of group. So the next 4 videos, this one and the next 3 videos, are going to be spent on building some intuition about what a group is and some of the properties it has. And it will be completely independent of anything related to cryptography. Okay, so let's jump directly into it by looking at the definition of a group. So on the one hand, at the left, I will put the formal definition of what a group is, and at the same time, I will give you here the intuition behind the formal definition, okay? Intuition. So let's start directly with the intuition of what a group is. A group is supposed to capture the abstract nature of a set of properties, okay? So a group is a set of transformations, okay? And the following 4 axioms are supposed to capture what a set of transformations should always satisfy, okay? So property number 1, well, first, a group is a set G equipped with a binary operation. So first, what is a binary operation? Binary operation, you can think of it as a box, delta here, which has as an input 2 elements, that's why it's called binary, right? Binary operation, G1 and G2, and gives as an output something, 1 element that is called G1 delta G2, okay? The idea behind this delta is that delta is composition of transformations, right? Composition of transformations. Okay, and now we can see what are the 4 properties that this set G equipped with this binary operation should satisfy. And the first one is that G should be stable under delta. Okay, so what does this mean? It means, if we look at the diagram here, that if we put as inputs 2 elements of the set G, then the output should again be an element of G, okay? If you write this with quantifiers, it's for all G1 and G2 that belong to G, then the output G1 delta G2 is again an element of G, okay? That's the first property. And this simply means, in intuitive terms, that if you take one transformation and you compose it by a second transformation, so you're doing one transformation then the other, the result, the whole thing can be viewed as a single operation, as a single transformation, okay? Composition of transformation can be viewed as a transformation itself. Confirmation of transformation. Transformations yields new transformations, right? New transformations. Okay, that's the first property. Second property that we need is that delta admits an identity element. Admits an identity element. The element. Okay, so if we write this precisely, what does it mean that it has an identity element? It means that there exists some element that we're going to call E, is a very particular element, such that for any other element that we take in the group, if we make the composition between them, E composed with G or G composed with E, then the result is simply G. So E is something that is basically changing nothing, right? And the idea here is that doing nothing, even though it's trivial, is a transformation. Okay? Trivial transformation, but it's a transformation. An actually important one. It's important to know what it means to do nothing. Okay? 3. Given this, all elements are invertible. That's the third property that we need. So what is the precise meaning of this? It means that for any element G of the group that you take, there, there must exist another element that we're going to call G minus 1, also belonging to the group, such that if you compose them in any order you want, okay, so G composed with G minus 1 or G minus 1 composed by G, this should give you the identity element, right? The intuition here is that one should always be ability to undo transformations. Undo transformations, okay? If you take an example with this pen, one transformation is to move the pen towards the right a certain amount of centimeters, and one should consider also the transformation, the inverse transformation, right, which takes this and moves it to the left and comes back to the initial position. So this should always be possible to do with any type of transformations, okay? And the fourth one here is that delta is associative. So that you know very well what it means. It means that when we write the parentheses, G1, G2, G3, then this should be equal to G1 parentheses G2, G3, okay? So in fact, the parentheses are not necessary in this case, okay? So this should be true for any 3 elements that we take in the group. And this from a intuitive point of view, what it means is that the only thing that matters when we're doing transformations is when you do them. This, then the second one, then this third one. It doesn't matter if we're doing in how fast we're doing these transformations, okay? So the only thing that matters is the order. Only time order of transformations, let's say, time order of transformations matters. Okay, so these are the 4 properties that a group should satisfy, and whenever you will be asked whether this structure with this operation is a group, you just need to check these 4 properties, okay? Let us now look at some examples. There are many examples of groups, so let us look at some examples of groups so that you see that you actually are very familiar with some of them. Okay, first example I'm going to give you is rotations on the plane. Rotations around the origin in 2 dimensions. In 2 dimensions, okay? So look at this. What I'm saying is consider this. Sorry, I need to open this again. Sometimes I have a small problem with OneNote, but it's easy to fix. So, okay. Okay, here we are again. Good. So rotations around the origin in 2 dimensions. Suppose we have this first shape, a triangle here that is here. The first thing that I can do is take this triangle and make a pi over 2 rotation of it, okay, here. So that's the transformation that you can do. And I can take a second transformation, and let's say it comes to be here, the triangle, okay? That's a second transformation. And of course, doing the first transformation, then the second transformation, you can view this as a one single transformation, which would be to take the first one and do this whole big rotation, right? So that's composition. Composition and stability If you do one rotation, then a second rotation, the result is a rotation again, and stability are okay. The inverse, so first, before the inverse, so we have 4 properties, right? Stability is okay. Second one is identity element. Now we need to look, is there some rotation that corresponds to doing nothing? And that, of course, is okay. Identity is the rotation of angle 0, right? So that's a rotation and it corresponds to doing nothing. Invertible, are all elements invertible or not? We'll look at these examples here. The first rotation, if I want to undo the rotation, it's simply, I just simply have to do the rotation in the opposite direction, right? Which is, of course, a rotation. Same for the second one, and same for the third one. So all elements are invertible because taking the inverse means only going in the opposite direction, right? And associativity, well, you know that it's okay as well. Okay, so that's rotations in 2 dimensions. And you can notice that, in fact, this has some bonus property that is not necessarily for it to be a group, but it is there. It's the fact that it's also commutative. And what commutativity means is that if you do the rotation of pi over 2 and then the rotation of pi over 3, it's the same as first doing the rotation of pi over 3 until here, and then a rotation of pi over 2. Okay, so if you want to make this precise, it means that for any 2 elements that you take, G1 composed with G2, it's equal to G2 composed with G1. So even the time order of the operations does not matter. But this is not true for all groups. This is just for this particular group, in which case this is called a commutative group. Second example, just to see one example of a non-commutative group is rotations in 3D. Okay, so rotations in 3D, they work exactly in the same way. If you take 2 rotations, the result is a rotation, so composition works. The trivial rotation of doing nothing is a rotation, so there is an identity element. They're all invertible by doing exactly the same rotation, but in the opposite angle, so it also works, and it's associative, okay? However, this rotation, so I'm just going to put idem here, because they work exactly as before. However, this is a non-commutative group. Non-commutative group. Okay, in the sense that if you take a rotation, let's say around the z-axis and a rotation around the x-axis, this is different to the rotation around the x-axis and then a rotation around the z-axis. Very simple to view with an example. At home, you can do this. You can take this, first do a rotation in the vertical direction. So for example, vertical, I move it of pi over 2, and then I do one rotation in the direction of into the computer, and it becomes this. The final result is the notebook that is horizontally with this black part looking into you, okay? But if I do the opposite of it, instead of starting by the vertical, I start by the one going into you, so I'm doing this, rotating like this, pi over 2, and then I do vertically like this. This is the final result. So as you can see, the results of the 2 rotations are quite different. So the order in which you do the rotations has an importance when you're in 3 dimensions, okay? So these are 2 first examples of groups. Of course, there are many more. So let's just discuss 1 or 2 or a few more, much more than 1 or 2. Third example that we can look here is what happens when the binary operation is the sum. So let's consider as binary operation the sum. And as you know, sum is a binary operation because it takes a number as an input, a number as 2 numbers as inputs, and yields as an output the number which is the sum of the 2, right? So the first question that you should ask yourself is, what is the identity element for the sum? So what is the number that if you add it to A, it makes no change? So the identity element is 0 here, right? Is the identity element. And plus is associative. Okay, so we have 2 of the 4 properties that are automatically correct here. Now what we need to ask is whether we have stability and whether all elements are invertible or not. So this depends on the choice of the numbers you're taking. If you're taking the integers or natural numbers rather, here, well, it's stable. If you take 2 integers, 2 natural numbers, and you add a natural number, it gives a natural number, so it's stable. That's good. However, we do not have inverse, because if you think of this, the equation 2 plus x equals 0, so x should be the inverse of 2, right? Well, this is equivalent to x equals minus 2, which does not belong to the natural numbers, okay? So n plus is not a group. Of course, if we just enlarge the set of numbers we take, and we take the integers instead of the natural numbers, or if we take the real numbers or the rational numbers or the complex numbers, these are all examples of groups. Okay? Okay, so that's one example, and we can ask exactly the same question. Instead of taking as operation the plus, we can take as operation the other one that we know, which is multiplication, right? Multiplication here. Okay, if we take 2 numbers a and b, the output is a times b. We can again ask, first, is this associative? Well, yes, multiplication is associative. And the second one, is there an identity element? Is there a number that when I multiply by this number, nothing changes, and this number is 1? 1 is the identity element, okay? So now we ask again. Let's take n, for example, n with the multiplication. If I take 2 natural numbers and I multiply them together, we have as a result, again, a natural number, so it's stable. But we again have a problem with the multiplication, right? Because if we want to do the inverse of 2, so this time operation is plus, is multiplication, and the identity element is 1. If we want to solve this equation, well, the result is x equals 1/2, which does not belong to the natural numbers. So that is not a group, okay? So it's not a group. And as you can see, since 1/2 is not an integer, same is true for z with the multiplication, right? Z with the multiplication is neither a group. If we want to have groups, then we need to consider the rationals, but you need to be careful to take away the 0, because 0 does not have an inverse, right? So if you take the rational numbers with multiplication, or the real numbers with the multiplication with the 0 excluded, or complex numbers, these are all groups. Okay? Okay, and perhaps final example, just to show you that this goes well beyond numbers. As well, you can consider functions from R to R. So this is usually called like this, the set RR, functions that go from R to R. You can compose these functions, right? You can, the exponential of x squared, for example, that's a way of composing functions. So the delta is composition of functions. It's a stable, right? If you take 2 functions and you compose them, the result is again a function. We have an identity element. Is it the function? Let's call it id for identity. That takes as an input a number x and gives as an output the same number. Okay. However, elements are not invertible. For example, the function x squared is not invertible, right? because it's not a bijection. The only functions that are invertible are bijections. Only bijections. Right? Bijections. That's almost the definition of a bijection is something that is invertible with respect to composition. Okay, so RR with this is not a group, but if you restrain yourself to bijections, let's call them bijections of R with composition, then we have a group. Okay, and one last example, which is almost the same with only a generalization to more than one dimension, is matrices. If we consider the matrices M square matrices with real coefficients and consider multiplication as the composition of matrices, then we have an identity element, right? Identity, what we call the identity matrix, 1 in the diagonals and 0 everywhere else. It's stable, right? If you take two matrices and you multiply them between them, the result is again a square matrix n by n. However, same example as before, not all matrices are invertible. Not all matrices are invertible. Not all matrices are invertible. Okay, so the Mn of R with multiplication of matrices is not a group. However, if you take just invertible matrices, which is usually denoted by GLN of R, with multiplication is a group. Okay, so this means invertible matrices, okay? And just to finish, notice that this is a non-commutative group. The product of matrices, as you know, the order matters. And it's the same for functions. If you take composition of functions, it's not the same to do x squared then exponential or exponential and then x squared. This is a non-commutative group as well. All right, so this gives you the first examples of to start becoming more familiar with the notion of groups, and in the next videos we will study more examples and more properties of groups so that little by little you become familiar with this notion.